Okay, so let me start with the chapter 1, mechanics of materials, stress and strain. Okay, so for this chapter, learning outcomes is number 1, define the relationship between the stress and strain. Analyze the stress and strain using related equations. Determine and analyze the deformation of rod of uniform or variable cross sections under one or several loads. Okay, and then determine the principal stress using equations and more circle method. Okay, this one including the chapter 2 already. Okay, so mechanics of materials is a branch of mechanics that study the internal effects of stress and strain in a solid body that's subjected to an external loading. The load from external, okay, outside. So stress is associated with the strength of the material from the body is made. Strain is the measurement of the deformations, either become longer, elongation, or shorter. Okay, so when you imagine this is the P, this is the body. When you have the outside forces, the P, pulling it outside, so it will make it long. So this is the difference of the elongations. Okay, so this is it, the effects. Okay, then you will have the stress. Okay, x direction and y direction, you pull it. Okay, so what are the effects? So you will have to calculate. Okay. Okay. So this one you see when you have tensional force, you're pulling it. You're pulling it towards the left and right. Okay, you're pulling outside towards outside. So you will have cracks right here. Okay, the tensional stress. You will need to be familiar with tension, compression, shear. Okay, compress is the force you push it. Okay, you push it, you compress it. Compressional. Okay, here you can see you have the compressional. Okay, and then you will have the shear. Shear is you have this left and right. Okay, you can see this is towards the inside, this is towards the outside. This is the stress of shear. Okay, wait. It's not moving. Okay, so type of forces. So number 1, okay, normal force. Just now I mentioned the tension and compression. This one is considered as perpendicular to the aerial, developed when the external load to push or pull. Tension is pull, compression is push. Okay, and then shear force. Shear force, you can see that one side is going upward, one side is going downward, or one to the left, one to the right. So the shear force lies in the plane of the area, in the plane. Okay, developed when the external load tends to cause the two segments of the body to slide. You have the slide when you apply force. Imagine you have force on here. This is a cantilever beam. You have the force pressure here. So it will cause the body to slide, right? You might have slide down. Okay, and then the force here will have to internal force going upward to support it. Okay, so other than that, you will have torque or torsional moment. So imagine when you manually sweep your toes, okay, you do the towel like you want to dry it out. Okay, you make the torsion force. Okay, so develop when the external load tends to twist, you twist. Okay, one segment of the body with respect to another. Okay, bending moment. Bending moment in chapter 3 you were going to draw. Okay, so imagine this is a beam with pin and roller connections. Apply force at the middle or at any other locations. So it will cause the bending moment. When you apply a force on a beam, so it will have the bend at here. So caused by the external load that tends to bend the body with an axis within the plane of the area. Okay, so stresses is the internal force exerted by one part of an elastic body upon the adjoining part. Okay, you can see the x direction, y and z direction in the 3D one. Okay, and then the dimensions, the unit. Remember this unit. Unit very important. Newton or millimeter square, kilonewton per millimeter square. There are many units. Also in the static dynamic, you already learned before the unit conversion. So make sure you are good with the conversion, the unit. Okay, so generally there are 6 dependent components of the stress at each point. So these are the stress for it. Okay, so type of stress, so you will have normal stress, or name it as an axial stress. Normal stress, you will have the stress going upward or going, okay, this is normal stress, going upward or going downward. Okay, and then the shear stress, tau, this is sigma. Sigma is F over L, the force over the area. Shear stress is tau. Tau is also force over air, but the force effect is different, like what I explained in the previous slide. Result when a force tends to make part of the body or one side of tend to slide. Okay, so type of the shear stress. Shear stress, you can see that. So this is the bone nut one. When you press, when you put it, the force going outside. Okay, so this is F over 2A because you have two area. You can see that here. When you push it here, okay, you will have 2P, two area. So this is one. Okay, one here. You can see one side. Okay, so imagine this one, only one surface, so it is F over A. If you have two surfaces, then it will be F over 2A. Okay, depends on the area. So bending stress. Bending stress, okay, is the bearing stress. Bearing stress is a type of normal stress, but it is involved the interaction of two surfaces. Okay, the bearing stress is the pressure experienced by the second surface due to the action from the first surface. Example, the pressure between the bone nut and the plate joint. Okay, the force applied, and then this is the place where it being having forces. So these are the formula. You go to example, it will be easier to understand this. Okay, so this is example 1, a hollow steel tube with an inside diameter of 100 mm must carry a tensile load of 400 kilonewton. Determine the outside diameter of the tube. If the stress is limited to 120 Newton meter, M Newton, this is the milli or mega Newton over meter square. Okay, sometimes the question will play around with the units, so be careful. Okay, so what provided information here is P is 400 kilonewton, which is equal to 400,000 Newton. Stress is 120 megapascal. M over n square is also m megapascal. So area, now you want to get the area. So area for the inside, the internal inside diameter, you already get it at 100. But the outside diameter, you don't know because this is a tube, right? So it's hollow. So you must get the area of outside minus inside. So the outside one is, the outside diameter is pi d4, okay, minus 1 over pi 400 power of 2 square root, 100 power of 2 square. So this is the outside diameter. This is the outside diameter and this is the inside diameter. Okay, so you solve it, that you cannot solve it yet because the d power of 2 is unknown. And this is what we want to find. Okay, so 400,000 is the P. Okay, is equal to 120 because we know is the stress is P over A, right? Okay, stress is F over A. So you have the stress is equal to P over A in the previous slide. Okay, so when you move it, so this is stress is equal to P is equal to 120, okay, times this A. Okay, so 400 is equal to this When you solve it out, you get D is 119.34. Okay, so stress is P over A. So P is stress times A. Okay, this is P. This is the stress. Okay, this is dA. So when you solve this equation, you will get D. I go to next example. Okay, so a homogeneous of 8 kg bars AB is supported at either end of M by a cable. Okay, as shown in this. So this is the bar from A to B. Okay, and then support by this bronze with L is equal to 4 and this steel. Calculate the smallest area for each cable if the stress is not exceed. Okay, so you've already given the sigma stress. Okay, it's not 900, it's not exceeds 90 megapascal in bronze and 120 in steel. Okay, so this one is bronze and steel. So how you solve it? Questions 2. So you have two rods, right? As shown in the previous one, you have two rods at A and B. So you will have a force. Okay, AB is supported by these two rods with different properties. So the stress is not exceed 90 megapascal, and the bronze is 120 megapascal for this stress. Okay, in bronze and also in steel. So these are supported, okay, by this one. So when you sketch it out, the free body diagram, you can see that W is 800 kilonewton, 800 kg. So you when convert it to Newton, you will get 7847. Okay, actually this one is typing error. 7847. So this one is not 800. This is instead of this value Okay, this typo. Have you guys noticed it? So PBR and PST are the steel and the bronze. So the shade by half. So you divide, okay, by 2, each support 3924 Newton. So for bronze, okay, you know stress is P over A. So P, okay, when you move the A, okay, towards the stress side, so P is equal to stress times A. So 3924 is equal to 90 times A, the area, okay. So you will get A is 43.6 mm when you solve it okay. The diameter you get it, the area you get it okay. Also you can get the diameter if you let's say you want to convert it, but here is 1200 area. Okay, so PST is also equal to stress times A. Okay, so 3924 is equal to 120 times A, so A is 32.7. Okay, so this is the example For example 3, okay, an aluminium rod is rigidly attached between the steel rod and a bronze rod as shown in figure 1.3. E1.3, okay, in this figure. X0 are applied at the position indicated. Find the maximum value of P that might not exceed the stress in steel for 140 megapascal, in aluminium of 90 megapascal, in bronze 100 megapascal. It's similar Okay, but then you can see that the P here is different. So this one is 4P, this is P, this is 2P. So how you solve it? Okay, so when you cut this part, okay, you can see that solution. You have part A, part B, C, and D. Okay, so when D here is 2P, you need to have a P to support this 2P. Okay, when you cut it here, you can see that when you have 2P, though, so P1 is have to have 2P. When you cut it here, the part B here, P2P is P2, you need to have 1P. Because here already have 2P, here 1P, so P2 is only equal to 1P because 2P and 1, here got 1P, here got 2P, so you only left 1P. P3 is 5P because here you can see 4p, here is 2p, here is 1p, then you get 5p. And then you solve it. Okay, so that one you can go through again. So I will move to next. Strain, strain. Just now is stress. So strain measure of deformation representing the displacement between particles in the body relative to a reference length. Okay, so this one you can see change of ratio of change in the length due to the deformation of the original length. So when you push it, okay, you can see the elongation is equal to the difference length for this one, okay, and then over this. The ratio is according to deformations. Okay, so this is the L, okay, the after the change the L, okay, this one times minus the original length over the original length. So it is dimensionless quantity. No quantity, and no dimension. Dimensionless because it's ratio. Ratio, you don't have units. Numerical values of strain are usually very small, especially for structural material which the ordinary undergo only small changes. So this one you can see this is a theory behind. So for normal strain, okay, normal strain in the deformation of a body which involve elongation or contractions. When a bar of length L and cross-sectional area is subjected to axial tensile force P. When you pull it, it will make it elongate. Okay, elongation will happen. Elongates. Okay, so the change in length divided by the initial length is the bar engineering strain. The symbol for strain is this one. This one. Okay, epsilon. The name of this is epsilon. The strain in an axially loaded bar is this one. Okay, this changes over the original L is the elongation, the epsilon. Okay, and then the shear strain. Just now this one is normal strain. Okay, this one is normal strain, but this one is shear strain. Okay, so shear strain you can see, okay, it's a strain which involves shear deformations. Okay, the body twists due to the torsion and distort cuboid as shown in figure 8.1, shown in this figure. Okay, strain changes the angle or the angles of an object and the shear cause in the line to rotate. So you will cause the protections, okay, you move and so on. This is the shear strain. So you can see that this is the AA, okay, AA over L, the original length. You can see this is it, and this is the AA prime. So this is strain. So exercise, another exercise here. The joint is fastened using two bolts as shown in figures below. Determine the required diameter for the bolt if the allowable shear stress for the bolt is, okay, the shear stress is 110 megapascal. Okay, so here you can see push 30 kilonewton by these two plates and 60 by this plate. So what you're going to do, okay, the shear stress by the double shear connections. So the shear stress is P over 2A because you have two plates. Okay, however, the joint fastened using two bolts. Got two bolts, okay, got two bolts. You have two surface and two plates, two surface here, and then you have two bolts. So is equal to tau is equal to P over 4A. So A is pi d power of 2 over 4. This one you already know this formula. Okay. Inside the final, the test, no equation provided. This one you need to know. Okay. The basic equation is P over A lah. But you need to, according to the examples, how many surface you have and so on. Okay. So A is 100 and this one is a stress just now. 110 is the, okay, is equal to 60 times 10 power of 3. 10 power of 3 is this one. 60 times 10 power of 3. Okay. So this is a force This is the area. So after you solve this, only one unknown, right? So you solve it, you get the D. Okay, to solve this, you need to know this one. How many areas, how many bolts and nuts. Okay, so now we go to stress and strain relationship. You have to learn the construction materials. So also you will learn the stress strain relationship. Okay, so this is a stress. Okay, either P, okay, or either the tau, and then this is a strain. Okay, so when you look at this, when you have the stress increment and the strain increment, you're going this way, okay, and then the Young modulus is this slope. Okay, this is the Young modulus. We call it E lah. It's equal to the slope, the rise over the run. X the y value of y over s lah is the slope. And then when this is the typical shear stress strain for this is for the concrete or either the steel bar lah. Imagine when you pull a material, you pull it, okay, until yield strain happen. Okay, when you happen the yield strain, then you're going down a bit, then going upward. And then this is the area of elastic stage. So this one, you will still back to the normal shape. So after the yield strain, you still pull it, you're still having applied stress on it. So it will elongate the strain hardening. So at here, strain hardening. You are not going to the normal locations. So once you achieve this one, the maximum, the ultimate load, we call it the ultimate strain. Ultimate strain happen, and then after you apply the load over the ultimate strain, it will happen the necking. Okay, so imagine the steel bar, you pull it, so it will necking, having the necking. So means that steel bar is having some necking like this. You consistent to pull it. Okay, so you will have this necking. After the ultimate load, okay, you pull it, so you will happen a necking, and then you will getting fat, getting weak, until fracture. Fracture means it fracture lah. Okay. So from this, you need to understand this relationship. This one you will use it forever. Even if you are doing the final year project for structure for materials, you're gonna face this and so on. Okay. So from the original O to the okay, so from the original O to the point called the proportional limited, the stress strain curve is a straight line. So the proportional limit is here. Okay, the material will return to its original shape. Like I said, this is the elastic stage. Okay, after elastic stage, you will move to the plastic stage, which is the strain hardening. After ultimate, you will go to the necking. Okay, 3 stages. Okay, so the stress strain relationship here, you can see we have the elastic limit, what I explained now, yield point, strain hardening, ultimate stress, and rupture strain, the fracture. So this one I already explained, you can go through again at your own time. So offset method. Let me check how many slides still. 24. Okay, I explain more. This chapter 1 actually is the easiest chapter among all 8 chapters. So this one I will go through today. Okay, and then I already recorded it, so later I will upload it and so on, so you can repeat again. So beside the steel, other materials such as aluminium, just now the graph is for the steel, not steel. The reinforced concrete, that normally you use the reinforcement, so the reinforcements are back from the steel. Okay, so besides steel, other materials such as aluminium, glass, brass, zinc, constant yielding will not occur beyond the elastic range. So these metals often does not have well-defined yield point. They don't have well-defined point. Therefore, the standard practice, okay, to define the yield strength for this metal is graphical produce called the offset method. You have offset method to get the yield stress. Okay, normally it's a 0.2%, 0.22 millimeter per millimeter. Okay, it's chosen from this point. This one, you plot it lah. 0.002. Okay, then you according to this slope, you offset it. Okay, so it's a line parallel to the initial straight line. This one, you offset this line 0.02, and then you will get the estimated yield stress. Okay, so move to next one. This example. Okay, a rod with a diameter 5 mm and length 100 mm is stressed slowly with the rod up to failure. So imagine you are doing this lab in the lab. So the result is shown in table E 1.8. Draw the stress strength curve and determine the modulus of elasticity, the E, yield stress, and stress maximum. So all these you need to plot into a graph. So when you plot a graph, you can see this. Okay, then you offset 0.2. It's 0.002. As just now you offset this one, you get the shape. So from this value you get the slope. You read this is the E, and the stress is the yield stress. Okay, and this maximum stress is this one. So you get all this from the graph. Any questions? This is the offset method. You offset with the value that provided 0.002. If no question, I move to next. Hook loads. Okay, stiffness. Modulus Young stiffness is a material ability to resist deformation. The stiffness of material is defined through the hook loads. Okay, E. Just now I mentioned the E, the slope. Young modulus is the slope of the linear elastic region, still in elastic stage, okay, of the stress strength curve. So E, modulus Young, okay, Young modulus is stress over strain in the straight line. You can see this is line, very straight. So stress is also equal to E lah. When you switch this formula, okay, you will get this. Okay, where E is the Young modulus, okay, a material properties, value of E is different. For different material are obtained experimentally from the stress strength curve. So you can get it from the experiment. Okay, different material, different Young modulus. Okay, from hook load the displacement can be derived. Okay, so stress is equal to E of E times strain. So you can get strain is equal to stress over E. Okay, so you can see that also when you do this, so the elongations is equal to, so the strain is equal to this elongation over L, right? So you reorganize it, it becomes PL over AE. Okay, so PL over AE. Okay, so Poisson ratio is the ratio. Now Poisson ratio, you have Young modulus, Poisson ratio, and then you have stress, you have strain, you have shear, you have normal stress, and so on. So many things in chapter 1. So here I can only explain to you all, but you need to digest it. Take time to digest it yourself. Okay. So Poisson ratio is the ratio of lateral contraction strain to longitudinal tension strain in the directions of stretching force. So you look at this formula, lateral over longitudinal. Okay, this is the ratio. Okay, so you can see that an example, a solid cylinder of diameter carries an axial load P. Show that its change in the diameter is 4 PV over pi ED. Okay, so this one, the load can be compressive strength or either tensile strength. Okay, if compression, then you will have the shorter one. will be shorter. If elongate with tensile strength. So the solution, so V is equal to minus the Poisson ratio. Okay, so is equal to negative stress Y over stress S if V is in the compression. Okay, so the stress, oh, why is it keep thinking? Okay, so the strain in y directions is equal to minus v times strain x. So when you solve this one, you will get this formula. So the y, okay, this I forgot how to pronounce this one. Okay, this one is equal to 4 times p times the Poisson ratio over pi times e, the modulus Young's times d. So you will get this value. Okay, you will get the y value. This here is y over 2 lah, but you get the y. Okay, so you have stress, you have strain, and what is all this for? Is for the design, right? So you will have design with allowable stress design. When you are doing the reinforced concrete design in your subject of design, you will have the safety factor lah. Okay, you have the safety factor. Of course, when you are constructing a house, a bridge, and so on, the buildings, you cannot design it without the safety factor. We must put some factor on it. Okay, normally it must be greater than 1. Means it, okay, must be greater than, must the design stress, okay, must be higher than the material, than the needed one. Okay, so safety factor here is a ratio of the failure load or to the allowable load. Okay, so failure load over allowable load. Okay, so for example, the building the stress is 150 megapascal, and then you allow only at 100 lah. If you want to put the safety factor at 1.5, okay, you cannot put the allowable and the failure with the same, because sometimes when you can see, imagine you are in Malaysia, people like to renovate, they like to extend the car porch, they like to have the extra upstairs, okay, rooms and so on. So if you put one, if you put the failure and the allow is the same, so cannot do any renovation at all, because if you add any load on it will fail, because it will be more, the failure will be more than the allowable load. So when you are doing the design and so on, we have factor of safety. Okay, other than that, you will have temperature stress. An object will expand when heated and contract when the temperature drops. Okay, heated will expand, contract it will, then when the temperature drop, it will contract. Since this is the effect of temperature on a member, the corresponding stress and strain is called temperature stress and temperature strain. So this is the equations. Okay, so the variation of the length due to the temperature, variation of the length from the temperature change depends upon its coefficient of linear expansion or contraction. Alpha is the change in length for unit change of temperature per unit original length. So this is the example. Okay, example 7. A steel rod is stretched between two rigid wall and two rigid wall, fixed support, carries with a tensile load of 500 Newton at 20 degrees. If the allowable stress is not exceed 130 megapascal at negative 20 Celsius, what is the minimum diameter of the rods? So assume alpha is 11.7 micrometer per m Celsius and the E is 200 gigapascal. So the conversions, okay, you need to put some effort on it. Go back to study again in static dynamic if you are weak in the unit conversion. So you can see that this is the tensile and the temperature, okay, and the steel. So when you resolve this equation, you calculate, okay. So stress, when you put this and then you get this. The stress is equal to alpha E, okay, times T plus P over A. So this is for the temperature, this is for the area stress. You calculate, you get the D. Okay. Oh, we have another half an hour. You guys have having any other having other class? No. Well, let me open to the assignment. So for the temperature one, I don't think I give you this one. Let me go to the assignment. Okay. So for assignment one, I already uploaded in the author system. You will have exercise 1.1 and AB, and also exercise 1.2 for this one. These two exercise. Okay, you after this class, you have to do it and upload in the author system in the assignment 1. Remember in the assignment 1 just now I show you the part that you have individual assignment. You do this and then we will discuss it in next Friday class.